Hey everyone, so we're going to continue our discussion about conservation momentum, and we're going to talk about something a little bit more complex than before. So recently, we just finished talking about one-dimensional conservation momentum, where objects come in pretty much in a straight line, and they should bounce off in, based off of their motion and whatever. But as we all know, uh, these one-dimensional collisions aren't exactly what we would see in real life. In fact, in real life, it's actually much more complex than that, where things will actually be going off in various different dimensions, in particular, two dimensions. For example, if you've ever seen a car crash, as you can see here, these are perfect examples of cars moving in two different dimensions and the momentum basically going off in very fairly complex ways. If you look at the car coming here, it's going, let's say it's going south, and this car is moving more to the west. So those two velocities are in different dimensions, and that's going to end up changing how we actually approach the momentum equation. Because as we learned when we did the kinematic stuff, we can't combine motion in one dimension with motion in another. Uh, just like how we did projectiles, we have to make sure that we kind of keep them separated. This isn't the only example, of course. uh, Billiards and pool balls. These are other examples where you have objects that will come in, and even in this case, where it kind of looks like it should be a one-dimensional setup with the ball moving towards another, because of the rounded shape and just general dimensions of the objects, we actually will end up with once again a two-dimensional setup or effect. So you could see it all in these cases. Now, the question is, how do we handle conservation momentum when we have two different dimensions and each dimension is completely independent of each other? Well, that actually leads us into what we're going to talk about. Now, the reason why I have to make this comment, because if you'll notice, we never had to worry about this with energy. And if you recall, that's because energy is a scalar, meaning direction doesn't matter. As long as we kind of went through and made sure that all our energy values were accounted for, then it didn't really matter whether I was going left or right or up or down. Energy basically turned into other energy, but momentum is a vector. So direction does play a part, and we have to make sure that we incorporate that. So what that means is, instead of just doing momentum before equals momentum after in a general case, we actually have to do it for both directions. We have to do it once for the x direction and then again once for the y direction. So we'd say px before equals px after, and py before equals py after. And basically, what we'd end up doing here is we would use the same equations we've done before, except instead of just putting in the velocity of the objects, we have to make sure that we plug in the x component of the velocities or the y component of the velocities. And we just need to make sure that all the objects have their components in. So this leads us into some complex scenarios, because first, that means that if we have objects moving at angles, whether it started at an angle or it bounces off at angles, just like how we had to do with the projectile setup, just like how we had to do with forces and all that stuff, we have to make sure that we break those velocities into components. So now each object is going to end up having essentially two velocities. They're going to have a y component velocity and an x component velocity that we plug into the equation accordingly. Another thing that kind of throws a little wrench into the problems is that uh, just like we saw in the last problem before, where because they gave us this additional information about the object being an elastic collision, it allowed us the chance to answer a problem with very little information provided. Now we have the same setup. By telling us that we have a two-dimensional setup, we now have two equations. We have the momentum in the x direction equation and the momentum in the y direction equation that we can use to solve problems. So it's going to be very common that you could have a two-dimensional problem with very little information because they expect you to use the two equations in conjunction with each other. Now, I could actually expand out. I said before that this was the equation that we would use. So if you recall, we had this expanded form for conservation momentum. m1v1 plus m2v2 equals m1v1 plus m2v2. Uh, because now we have to take into account x and y directions, essentially what I'm going to do is add x component to all the velocities, or a y component to all the velocities. Now, uh, there's good news and bad news. Like I said, the bad news is questions can get very complex. Like I said, now we can have setups where we have very little information. You're going to have to break up things into components. It can get really hairy. The good news, there's a really good chance that you won't have to do those problems. And most of the time, if you're doing a two-dimensional setup in this AP course, it is more common, more likely than not, that you're going to be seeing a problem where a lot of these terms are going to drop out. So I actually jokingly call this the Dora the Explorer equation, because essentially when you go through the equation, you're going to ask yourself, does this go to zero? Does this go to zero? And you'll find that a lot of terms drop out because we're going to be doing very simplistic setups for two-dimensional motion. All right. So I just want to kind of give you an example of what I mean by that. So here is one example of a two-dimensional motion problem that you could have. So we have one ball moving forward, and it's going to strike another ball, and they bounce off in these directions. So in this case, what we would have in the initial setup, this was the only one that had momentum, and it only had momentum in the x direction. So the equation up top, this term would drop to zero because initially this object had momentum, but this object was at rest. In the y direction, both of these terms would actually have dropped out because, again, let me try and change this, because this had no y velocity. So the only velocity it had was x velocity. So right off the bat, we can see that this entire setup actually basically boils down to the x direction having only 3 terms and the y direction having the final 2 terms for after they collide. All right, so that's one example of how a question could be made a little bit simpler by having a lot of terms dropping out. Likewise, let's see if I could erase all of it. All right, let's start this over. Another way that they could set up the problem is have it something like this, where now in the x direction, one object carries the x momentum, while the pink one was moving vertically. In the vertical direction, this one drops out because it was moving horizontally, and only the red one carried the vertical momentum. And then we'd end up having 2 more terms dropping out. And if I want to actually make it even more simplistic, I could turn this collision into, I guess I can't make it into a completely inelastic collision, but I could do something like this where now, they're moving together with the same velocity. So these terms will actually combine so that it's m1 plus m2 times v2x and m1 plus m2 times vy. So again, there's a bunch of different ways that they could set up this conservation momentum in 2 dimensions to make life a little bit easier for you. So we'll do a little practice question. So work on this yourself, pause the video, and we'll go over a second. All right. So just to give a visualization, this is what's happening. We have a car that's going 30 meters per second going north. We have a car that's going 20 meters per second going east. Both of them are 500 kilograms. Again, we want to do conservation momentum in both x and y direction. So let's start with the x direction. So in the x direction, this first car has a velocity of 20, and this car has a velocity of 0, because this is only moving in the x direction and this is moving in the y direction. So this has no x component. So when I set up the conservation momentum, I have 500 times 20 plus 500 times 0, and I'm going to have it equal to 1,000 v because they stick together. So they're 500 kilograms combined together, and they're going to have the same final velocity. So when I solve this, I get that the x component is equal to 10. All right. Now that I did the x direction, I'll do the y direction. So again, I do the same thing. In the y direction, this is 0 because, again, it's only horizontal. In the y direction, this is 30. So once again, I do 500 times 0 plus 500 times 30. And again, it's going to be equal to 1000 Vy because they stick together. I end up getting that the y component's 15. Now that's not my, these aren't my answers because it wants the actual velocity, not the components of the velocity. So I'm just going to do Pythagorean theorem, where the a, the b, and the c are the x component, the y component, and the final velocity respectively. So plug my numbers in, and in the end I get 18 meters per second. So I end up figuring out what the velocity is, and if I wanted to take it one step further, I could also find the direction of this velocity by using SOHCAHTOA. This is pretty much it for conservation momentum in 2 dimensions. Like I said, it's really not that complex. You'll probably see a few more questions in class where we kind of will see, how it would look as a multiple choice question. But for the most part, like I said, even though the questions can get tricky, the likelihood of you seeing a 2-dimensional problem that you'll have to calculate is very low. I just wanted to make sure that I said it just in case you saw one. Even if it was the simple case, I wanted you to at least be aware of how you would handle a 2-dimensional setup. All right. If you have any other questions, feel free to let me know. Otherwise, good luck and have a great day.